Welcome to this explainer on the history of life on Earth. I want you to picture something for a second. Imagine a toxic, boiling rock surrounded by highly acidic oceans and a completely unbreathable atmosphere. Pretty bleak, right? Now, look out your window at the Earth today. It's teeming with billions of complex, incredibly beautiful species. So how on Earth did we get here? How does a planet transform from a barren, hostile rock into this thriving, biodiverse biosphere we live in today? Well, it's an absolutely epic story of dramatic changes, brutal environments, and fascinating adaptations. And we're going to break it all down. Here is how we're going to tackle this. First, we'll look at the spark of life. Second, climate and competition. Third, the oxygen revolution. Fourth, Earth on the move. And finally, number 5, the geological timescale. Let's dive in. Section 1, the spark of life. Let's rewind the clock way back to primitive Earth and look at the raw, non-living ingredients we had available to actually create life. Seriously, how does a barren planet of water and rock transform into living matter? Early Earth was frankly a terrifying place. We had water, sure, but it wasn't fresh or drinkable. It collected in huge, highly acidic oceans. We had an abundance of minerals scattered around, things like sodium, magnesium, and potassium. And we did have an atmosphere, but it was incredibly dense, choked with carbon dioxide, methane, and sulfur. And here's the kicker. There was almost zero oxygen and absolutely zero living things. So how exactly do you take this toxic, non-living chemical soup and turn it into life? Enter the famous Urey-Miller experiment. This was a brilliant piece of science where researchers essentially tried to build primitive Earth in a lab to see if they could generate the building blocks of life from scratch. They set up a system that boiled water to simulate ocean evaporation. As that water vapor rose into a chamber, they pumped in those nasty primitive gases we just talked about: methane, ammonia, hydrogen. And then they introduced a spark. You see, in nature, lightning is a phenomenally powerful force, literally strong enough to split chemical elements apart. So scientists shocked this vapor mixture over and over to simulate early Earth's lightning storms. When they eventually condensed and collected the liquid that formed, the results were mind-blowing. The electricity had broken down those basic gases and recombined them into carbon, hydrogen, nitrogen, and oxygen to form amino acids. That's huge, because amino acids are the primary building blocks of proteins, making them the very first true building blocks of life. Moving right along to Section 2, climate and competition. Now that we have the raw origins of life, we need to meet our first great chef, a massive non-living factor that forced evolution into high gear. We hear the term Ice Age a lot, but putting the sheer scale of a prehistoric Ice Age into perspective is staggering. We aren't just talking about a really harsh winter. On prehistoric Earth, unimaginable portions of the entire globe were completely locked in solid ice. We're talking massive ice sheets stretching all the way down through the United States, blanketing the majority of Europe, and covering huge chunks of China and Russia. Compare that to today, where we just have relatively tiny amounts of shifting sea ice up in Greenland and the North Pole. So what does a massive freeze actually do to life? It triggers a brutal planetary domino effect. First, global temperatures plummet, meaning any species that can't handle freezing cold faces immediate extinction. Because of this, everything that survives has to flee toward the warmer equator. But think about what happens next. Suddenly, you have a massive number of species crammed into a much smaller, warmer area. This extreme high density causes competition for food and space to absolutely skyrocket, meaning only the strongest, most adaptable species are going to make it out alive. And the dominoes keep falling. Because so much fresh water is physically trapped in those giant ice sheets, global rainfall completely drops off, leaving the planet with a much drier climate. Consequently, ocean levels fall drastically, exposing new dry coastlines and totally rewriting coastal ecosystems. Everything changes. That brings us to Section 3, the oxygen revolution. Our second major evolutionary chef is something we use every single second without thinking: a sudden, massive shift in global oxygen. As we established, primitive Earth had virtually no oxygen because, well, there were no plants. But then this incredibly lucky evolutionary leap happened. A larger primitive cell swallowed a smaller bacteria that survived on those early toxic gases. A bit later, it swallowed another small bacteria, this one capable of photosynthesizing. But here is the ultimate plot twist. Instead of just digesting them for a quick snack, they teamed up. It became a perfect symbiotic loop. The photosynthesizing part cranked out oxygen, which the other bacteria desperately needed to survive. In return, that bacteria pumped out carbon dioxide, which fueled the photosynthesizing part, a completely self-sustaining microscopic factory. As trillions of these tiny factories multiplied and clumped together, they formed the very first algae, and eventually plants, which started pumping the first real breathable oxygen into our atmosphere. And let me tell you, this oxygen revolution was a complete game changer for biodiversity. At one point during the Carboniferous period, global oxygen levels exploded to roughly double what they are today. Now, because insects absorb oxygen directly into their bodies through their skin, this massive surplus of oxygen acted like a biological supercharger. Picture walking outside and seeing a dragonfly, but instead of being the size of your palm, it's the size of a cat or a small dog. Seriously. This almost absurd level of biodiversity happened simply because life was handed an abundant new resource and ran wild with it. All right, on to Section 4, Earth on the Move. We've covered climate and oxygen, but we cannot ignore the incredibly violent physical geology that literally reshapes life. You know, the ground beneath our feet feels totally static, but the Earth's crust is actually highly active. Through continental drift, our massive continents are constantly sliding across the globe over millions of years. And as a landmass slowly shifts into a completely different latitude, its local temperature and rainfall undergo radical changes. To put that into perspective, the Sahara Desert used to be a lush, thriving rainforest before continental drift moved its position on the globe. Add brutal earthquakes to the mix, which can literally tear entire land masses in two. When that happens, species that used to live together are violently separated, permanently isolated, and forced to adapt to entirely new climates. If they can't adapt, they die out. And if shifting continents weren't enough, primitive Earth was incredibly volatile, packed with severe volcanic eruptions. When these supervolcanoes erupted, they didn't just spew lava, they blasted enormous, thick clouds of heavy ash high into the atmosphere. We are talking about ash clouds so dense, they physically blocked out the sun, sometimes for years. Without sunlight, global temperatures plummeted into the freezing zone. Worse, plants completely lost the ability to photosynthesize. No photosynthesis means the entire food web collapses, and oxygen production halts. This 1-2 punch of cold and starvation triggered horrific mass extinction events, wiping out countless species across the globe. Finally, Section 5, the geological timescale. We know the ingredients, we know the chefs. Now let's look at how Earth's biological menu was actually served up over the millions of years. When scientists map out the history of life, reading from the oldest rocks to the newest, they divide this immense timeline into eras and periods. It's actually pretty simple. Think of an era as the big picture, a massive, broad chunk of time defined by whatever organisms were dominating the planet, like the age of reptiles or the age of mammals. A period, on the other hand, is a specific subdivision within that era. Periods are the dramatic plot points. They mark sudden major shifts, like a catastrophic mass extinction, or the sudden debut of a major new player, like the very first fish. Let's walk through it. Way back, over 650 million years ago, we have the Precambrian era. This is a bit of a mystery era because life was mostly simple, squishy, soft-bodied organisms like worms that didn't leave hard fossils behind for us to dig up. But move forward to the Cambrian period and boom, an absolute explosion of diversity. We get complex organs and the very first creatures with actual backbones. Jump to the Silurian period and life officially crawls out of the water. We see the first vascular land plants taking root. But remember, evolution is a rocky road. We eventually crash into the Permian period, which brings a catastrophic mass extinction that wipes out an estimated 95% of all life on the planet, just completely gone. But life bounces back, right? Getting closer to today, the Triassic period introduces the very first early mammals. But they had to keep a low profile because the Jurassic period arrived and was completely ruled by massive dinosaurs. Next is the Cretaceous period. Now, this is famous for being the end of the dinosaurs, but it's equally important because it brought us the very first flowering plants, and with them, the first pollinators like bees. And here's the wild irony of Earth's history. After the giant reptiles were wiped out at the end of the Cretaceous, the playing field was finally clear. It opened the door for our current era, the Cenozoic era. With the giant predators gone, our tiny mammal ancestors were finally able to survive, multiply, and eventually take over the entire planet. And that brings us right up to the present day. But we can't wrap up this explainer without looking forward. Everything we've seen shows that life on Earth is entirely at the mercy of ever-changing ecosystems, fluctuating temperatures, and shifting continents. So we have to ask ourselves, we've had an era of aquatic life, an era of giant reptiles, and our current era of mammals. When the climate and continents inevitably shift again, rewriting the rules of survival, what will the next great geological era look like? What new, bizarre organisms will rise up to take the crown? Keep that in the back of your mind next time you step outside and look at the world around you.